Okay, so right on the Monday, 6, 7, 8, November 8th, right after your presentation, I'm asking you to do, I don't know how to call it, which number to assign. It's like a textual homework without problem solving. Just summarize what you've learned from the class, and it's much less details that is provided in presentations. Maybe like one sentence or one equation per question. So it shouldn't be too long. Why we should bother and spend your valuable time on this thing? Because when we start projects, this method of code will be main tool, and I would feel much more safe if I'm confident that you all are operating and understanding what is going on, and it will help you to go through the projects easier. This is something you are working right now, and that we will hopefully grade in class on coming Wednesday. And here is the stuff that we will grade in 2 weeks, also on Wednesday. So the subject that we are starting right now, harmonic oscillator in basis of discrete states as vectors and matrices, will provide background to complete this homework. So right now there is no much reason to look on it, because we do not have actual material which this homework is appealing to, but I just want to play open cards. So when we finished our meeting last time, we arrived to the stage where I better talk without appealing to equations to be more general. So we are speaking about harmonic oscillator, which is atomic vibrations. We are looking on the vicinity of equilibrium when one can consider everything harmonic, and we are applied annihilation operator to find ground state, and then creation operator to ramp up and get eigenstates. It was main achievement of last time, and in this aspect, our course goes along with anyone in the world teaching similar course. The concept of ladder operators, meaning the straw man or just our focus, moves from lowest possible state, one rung up, one state up, or down. So those are symbolic operators that transmit us up or down between states which are neighboring in energy and in the number. And this creation and annihilation operators are expressed in terms of position and momentum, right, as linear combination. And there was an interesting observation. If we apply creation and annihilation operator to, well, creation to a certain state, and last time it was state number 1, we got state number 2, but upon carefully processing normalization, we found that actual normalized eigenstate number 2 and result of operating creation operator of state number 1 differ by a factor of square root of 2, right? And then we decided to believe that this trend will continue. We just left the proof that by applying a creation operator to state number n, we will get state number 1. But in addition, due to, we will, in comparison to normalized state n plus 1, we will get a factor square root of n plus 1. I do not know how to communicate efficiently with those who are on Zoom. I know that those who are in class in minority, but at least I will ask your support. Okay, good. If someone disagrees or wants more questions on Zoom, please stop me and just raise the voice. Raise the voice is better because if you type something, I could miss it. Okay, so this is the main outcome of the last meeting, and right now we are going to do 3 mathematical operations. I'll try to go carefully through them later, but it's better than that we achieve agreement on what they are, because math is not a style typical humans are thinking. So what is the goal? Maybe not the goal of the universe, maybe not the personal goal of each one in the class, but at least my goal is delivering this material. There is an experience from like previous generations that solving problems in matrix form is much easier. Sometimes it is easier for humans, and always it is easier for computers. It's just there is no other way. And it is very standard approach in any area of STEM sciences to convert problems that we need into form of vectors and matrices. Then many problems can be standardized. And specifically in physical chemistry, it is very appropriate. So we already have solution of time independent Schrödinger equation in this graphical distributed functions. And now we want to speak about functions only as expansion coefficients in vectors, right? Because arbitrary wave function will be a superposition of eigenstates. If we follow this path, then we will need to convert all operators that play any role for this subclass of problem into matrix form. And converting operators from differential into matrix form is related to the process of taking matrix elements. Basically, same as we do for finding expectation value. So we do create a sandwich where one eigenstate is from the left, another eigenstate from the right, operator in the middle, and then we get a number, right? And if we repeat this operation as many times as many pairs of eigenstates we have, then we will get the full translation, conversion of a differential operator into just set of numbers, as matrix elements. In this language, everything goes really easy. So let me check if this idea of converting operators into matrices gets any positive feedback from your mind and brain. Yes, no, more or less. Okay, okay. let me try to ask those who are okay. Lola, thank you for supporting. You see, Lola selected thumb up. So please speak or just type, if possible, you're okay. Thank you, Sibel. Thank you, Lola. So we have 4 out of 7. Oh, okay. So everyone except Joshua already made thumb up. Joshua, do you like an idea of converting differential operators into matrices? Thumbs up. Okay. Full majority. Thank you. So, and we need to practice this conversion of differential operators into matrices for three operators: creation operator, annihilation operator, and operator of total energy. Basically, if we complete it, we do not need anything else. It will be enough for today. So if I would be bald, white hair, old-fashioned representative of 18th century, I would practice finding of matrix elements by taking the operator and then multiplying it by like Gaussian function times polynomial for one matrix element and Gaussian polynomial times another matrix element, and taking this integral as many times as needed, which originally people were trying to do, but it is only a way to torture those who derive. There is much quicker and shorter way. So we are going to use the philosophy of matrix elements, but we are going to combine it with our previous agreements. First, that raising operator does nothing but converts state n to state n plus 1, and that it accumulates a factor square root of n plus 1. So instead of redoing all operations, we can just take this result, which is basically extracted from similar operations, but we just do not want to repeat it. So creation operator, right? Eigenstate number n and eigenstate number n. If we apply creation operator to the right, to state number n, it will make it convert it into state n plus 1, right? And accumulate a factor. Then the factor can be put outside of the sandwich, Bryant cat, and then inside the we have a like empty sandwich, no butter between two slices of bread, and we have two different indices, m and n plus 1. I don't remember if we proved it for harmonic oscillator, but it is a quite general property, and if it doesn't fulfill, then it is either bad eigenstates or people start discussing it if they not fulfill these properties. But typically, if no one objects, if no one starts speaking as a special case, all good basis states, all good solutions of Schrödinger equation obey the property of orthonormality, right? Which means convolution of Bryant cat should be either 0 or 1, right? So there will be 1 if two numbers here coincide, and will be 0 if these numbers do not coincide. Let me make another tour of checking. So would you please confirm that idea of Bryant cat sandwich should be either 0 or 1? And this idea doesn't surprise you, Joe? Okay. Sibelius, thank you. Lola, thank you. Nate, thank you. May, thank you. Joshua, do you like the idea of sandwich giving either 0 or 1? I don't know if I should. Oh, let me make it in a way. Oh, and there is Alison. I didn't notice you. Alison, did you make thumb up or you didn't? Okay, then since I do not have the full quorum, I'll better say something because we should be all on the same page. Okay, just repeat, same thing. The solutions of Schrödinger equation in form of functions always obey property of orthogonality and normalization. So each integral of wave function squared must be 1. And if you take wave function with one number and wave function with another number, you multiply them and integrate, this result will give 0 if they are if those are different functions. So this is called orthonormality property, and I'm just repeating because not everyone raised them up. So if it induces properties, look for it in like Wikipedia textbooks or send me an email. The sandwich, this bra and cat angular brackets n and n identify quantum state m, quantum state n, and the result of this convolution, which is in old-fashioned style, will be just integral, will be 1 if the numbers coincide, 0 if they don't. And we are going to use this property in the next line. And if you do not like property of orthogonality, please convince yourself to start liking it, because it's one of the minimal fundamental concepts without which we cannot go further. So this stuff here must be either 0 or 1, and we can write it as Kronecker delta m comma n plus 1, which means if integer number m equals n plus 1, it will be 1. If it will be something different, it will be 0. So we can just write it this way. Now there is a question. We were wishing to represent operator as a matrix. So which matrix corresponds to a delta function? Yes. Can you draw it in the air or describe verbally what is identity matrix?
It basically just has like ones going down the diagonal and zeros everywhere else.
Excellent. Yeah. Thank you, Joe. So it will be identity matrix if you have m and n, if simple index. But what if we raise one index? How does this identity matrix will change? There is a way to prove it. Just set up like numbers from 1 to 5, and then numbers and make matrix 5 by 5, plug in different elements, and look what we will get. But I can it will be a little discovery, but you see that instead of main diagonal, it will be subdiagonal, right? So here is what Joe helped us. Identity matrix with ones on the main diagonal and zeros everywhere else. And if we change one index, then instead of main diagonal, it will be upper subdiagonal. And since we do have, one can prove it just by plugging in numbers. And then this square root factor will mean that we will have escalating square roots instead of ones along this diagonal. So we have 30% done for today's meeting. What if we have annihilation operator, lowering operator? We may have discussed it before, that it is a conjugation and transpose. They're conjugated, and we can just flip the operator in respect to main diagonal. Or if we don't like, we can repeat the same derivation as we did before, and then for number m, it will convert to n minus 1. So the idea is that if you do annihilation, it will use the lower subdiagonal. Let's go back and maybe just do a little example. So if we have m equals 2, and n equals 1. So then we will have non-zero element. And for m equals 2, any other values of n will be zeros, right? So we parse aside. If you select m equals 3, then in order for this delta, Kronecker delta will be non-zero, n plus 1 should be equals 3, so n will be equal to. So third column, second row. Okay, and we are 60% done. At the beginning, I cannot load my responsibility on your shoulders, but at least no one was protesting. The idea was to convert 3 elements from the differential form into matrix form: raising, lowering, and Hamiltonian total energy operator. So the total energy operator in matrix form will be frequency factor, and then on the main diagonal, it will be escalating numbers: 1/2, 1 plus 1/2, 2 plus 1/2, 3 plus 1/2, which means energy of ground state will be 1/2 times this number. Energy of first state will be 1 plus 1/2 times this number. Energy of the second state will be 2 plus 1/2 times this number. Make sense? And you already touched this question of linguistic terminology and naming of the procedure. So finding solutions of eigenvalue problem is often called diagonalization, because upon finding eigenvalues and converting matrix into the basis of eigenstates, the original matrix becomes diagonal. Did you hear something before? More or less. So if it is not pronounced explicitly, it may create confuse, because when you solve eigenvalue problem, you get only vectors and eigenvalues. But if one composes of this eigenvectors a matrix, then transposed matrix, put your original matrix between them, multiply these 3 matrices, one will get something diagonal, which means linear transformation into eigenstate basis. So in the eigenstate basis, each matrix is expected to be diagonal. So in the basis of eigenstates, Hamiltonian harmonic oscillator in matrix form has diagonal form. So it's not a big surprise. And values here are just eigenenergies. So one would be able to guess this answer, this solution, even without any raising and lowering operators. It can be extracted from the common sense, but I plan to show a path, a way how to arrive to here by a little derivation. Okay. Whew. And actually now, about 15 minutes before the end, we start actual lecture. So we do have raising operators and lowering operators. They are linear combinations, and later on, if we add them, we will get and do some work on factors, we will get position operator. If you subtract, we'll get momentum operator, and one can express any operators, position, momentum, kinetic, potential energy, total energy, in terms of the raising and lowering operators. So when we were designing this raising and lowering operators, we used a property that we design those operators in such way that multiplying these two operators by itself, we should reproduce Hamiltonian, right? You remember? Okay. And now, although it is kind of set up, it's more like exercise, but we are going to plug our matrix, our original idea when we set up this functional form and when we designed correction and annihilation operators, we were speaking about everything in terms of differential operators, about position and momentum. Now we do have a conversion of differential operators into matrix form, or this bracket form, which is identical to a matrix. By looking to your eyes, I see that this notation may surprise you. Is it right? Okay, yeah, I was kind of rushing through, so I'll better delay a little bit, speak about these two lines, and then check that everyone feels happy about it. So, a few words more. When you were making your presentations number 2, I think it was, I don't remember exactly names who was doing what, but I think it was Josh who was introducing the dyadic products, right? So if you multiply vectors in the form of row by column, we obtain a number. And if you multiply vectors in the opposite column by row, we obtain a matrix. Okay. Now, the cat is typically this angular bracket to the right. Cat corresponds to column. And the angular vector to the left corresponds to a row. So if we would have standard sequence, row by column, bra times cat, we would obtain a number, right? But if you swap their order, if you multiply cat times bra, it will be a matrix. So this notation in the top line corresponds to a matrix. So it is a Dirac notation, algebraic representation of a matrix. So from state number n, we are getting state n plus 1. And in front of this operation, we are getting this factor n plus 1. So if I'm going to quickly jump a few slides back and then return here. So this element would correspond to, so when this row of this matrix acts on a column that has I might have lied to you. I might have swapped. This should be when upper diagonal is used, it looks more like annihilation. And creation when it is lower subdiagonal. Okay. So when we do have an element here. And we have a matrix that would correspond to the ground state. Right? We practice row by column. And in the first element, we get nothing. We practice row by column another time. Should be one that's correct. Okay, we practice row by column once again, and we get square root of 1 here. And for the rest, we get 0. So this row, this column vector was corresponding to state 0. This corresponds to state 1. Right? So by practicing, and right now I don't care what was in the rest, so I can populate it with. But this matrix corresponds to conversion from 0 to 1. And we can write it in the following way: 0, 1. The operations that we just did. So bra and cat. If we rethink of it as binding together this bra and this cat that originates from original vector, they cancel and give us factor 1. And then as a result, you get number 1. Make sense? Whew. Okay. Let me quickly check if it makes any sense to those on Zoom. So thank you, Sibel. Thank you, Nate. Thank you, Lola. Thank you, Mai. Alison and Joshua, please. Oh, okay, I see something in the chat line. Joshua, thumbs up. So, Alison, please speak up if you need, if you have some questions, if you need more explanation on this concept. Or send an email if we need to discuss it in more details. Okay, returning back to where we were. So the top line converts junior to senior, n to n plus 1. Therefore, it is creation, right? Next line corresponds senior to junior, or whatever, more higher number to lower number. And therefore, it is an initialization operator, right? And we do need to plug in these two definitions into here and see what happens. And we have 6 minutes for this. So I'm going to forget about h bar omega and 1/2 because they're trivial, and just product of these two operators would be enough for 5 minutes. So first we have a dagger. Second, we have a without dagger. Here we go from lower to higher. Here we have from higher to lower. And each of them does, I should face camera. Each of them has the factors. So summation over m doesn't affect n, therefore we can move it up front. So we have 2 summations, all factors, and then a combination of 4 vectors. Arrow right means column, arrow left means row. So row, column, And there is a way to simplify this equation. Anytime we see this sandwich construction when left and right come together, one has to practice which property? Anyone wants to help? There's a way to get rid of two-way functions. If bra and cat are coming together, they can be converted to 0 or 1 by the property which is called orthogonality, right? So we can focus on these two middle portions and say if n equals m minus 1, then it will be 1, otherwise it will be 0. So we are replacing this encircled thing into delta n comma m minus 1. And now we do have two summations, delta function, and then the junk. Once upon a time, I was sharing my personal positive memories about linear algebra. When summation meets delta function, they both disappear, right? Let's check if it applies here. So we have this summation over n, and we have this delta function n comma m minus 1. So we can remove summation over n and keep only those elements when n was equal to m minus 1. Or if we remove n, then we can tell that m minus 1 was equal to n, right? And then we can move minus 1 onto other side. So m equals n plus 1. Okay. So we replace m to n plus 1 here, right? We replace m to n plus 1 there. And I was lying, I will remove not summation over n, but summation over m. So by doing this replacement, let's go back once again. So first, cat was n plus 1. Last cat will be also n plus 1 because of this substitution. This panel. And as a result, we do have summation over n only. Here we have cat and bra, both of which are n plus 1, right? And here we have factors. Also, because of substitution, it will be square root of n plus 1, square root of n plus 1. Square root times square root will be just stuff inside. And also, if we consistently replace n plus 1 by another index k, the progression to the side of infinite values will not change, right? So we replace this square root n plus 1, square root n plus 1 by k, and this cat and bra by cat k, bra k. Now, which matrix does this correspond to? So it is an operation that changes eigenstate number k into an eigenstate number k, right? Which will be an identity matrix. So if you wouldn't have this k factor here, this would be an expression for identity matrix. But we do have ramping up values on the main diagonal. So it will be like 0, 1, 2, 3, 4, 5 on the main diagonal. I think we already done this procedure. And if we take into account factor h bar omega and add 1/2 to each of the numbers, so if one has a number in the expression for matrices, it means this number is multiplied by identity matrix, which means to each of the diagonal element of the second matrix, you should add the same number. And as a result, we will, so our Hamiltonian will be h bar omega up front, then summation over k, and then we should move this 1/2 into there. Which will give us this matrix. Thank you for your patience. Meeting is dismissed. Have a nice weekend. I'll stay here if any questions is needed. Sorry for taking your minute. Whew.